Alright, separation of variables for the wave equation. Remember, the wave equation is second derivative is c squared times uxx. And let's just say that the endpoints are fixed, so u0t is 0, and u of, let's say, 4t is 0. And then we're going to let u of x comma 0 as x times 4 minus x, so that the graph looks like that. Okay? And because this is a second order differential equation in t, we also have to provide ut x0. And just to make it simple, let's call this 0, because, which means that initial velocity is 0. So you have this as your initial condition, and think about fixed string, okay? And you pull the string in this format and you release it. Because it's released, initial velocity is 0. And what would it do? It's going to do this. It's going to go forever. Okay, so we're looking for that solution. Again, we just solve the boundary conditions and the equation itself, which is called the separation of variables. SoV means separation of variables. So solution, we set uxt as a function of x times the function of t, and you plug it into here, which gives you x t double prime of t. Because it's a second derivative with respect to t, it will be x double prime of t equals to c squared x double prime of x t of t. Okay? It's very similar to the heat equation separation of variables. What should you do next? Divide both sides by c squared
xt.
xt. So that on this side x cancels out, on this side t cancels out, c squared also cancels out, and the result is that you have a function of t equals a function of x. When can that happen? The only way that could happen is if they are equal to a constant. We decide to call that constant as negative lambda. Good. So we call it negative lambda. And then we also apply the boundary condition to here, so that if you plug in 0 and t into here and there, you get x of 0 times t of t has to equal to 0, which implies that x of 0 is 0 or t of t is 0, but this yields trivial solutions, so we don't like it. Same way, x of 4 t of t has to equal to 0, because that's the right endpoint condition, the right boundary condition, and we plug in 4 into x, t is t. So that means either x of 4 is 0 or t of t is 0, but again, this is no good because these yield trivial solutions. And then we take this much, rewrite that by multiplying x both sides and moving negative lambda x to this side, and you get x double prime plus lambda x equals to 0. And we know very well what these mean. This is the Sturm-Liouville problem, where we know that only for certain values of lambda you get non-zero solutions, and that's when lambda is equal to n squared pi squared over 16. Well, this is another problem that could be on the exam. You have to solve this for lambda positive case, lambda 0 case, lambda negative case. Well, lambda negative case doesn't happen for this case. You can skip that, but you have to figure that out for each cases. And you have that for your homework, so if you have done that, you should know how to do it. Okay. Also, you can refer to the practice problems for that. Okay. So at the end of the day, this is what you're going to get with y. No, x of x equals to sine of n pi over 4. So these are the eigenfunctions, these are the eigenvalues with n equals to 1, 2, 3, and so on and so on. Okay, now the difference is, now what about t double prime of t over c squared t? See, once you take that n squared pi squared over 16 and you plug it in here, you get t double prime over c squared t of t equals to negative n squared pi squared over 16. So if you move this to the other side and you bring this entire thing to the left, what you get is t double prime plus, let's see, c squared gets multiplied here, so it's c squared n squared pi squared over 16 t equals to 0. Okay. So it's a second order differential equation with respect to t. And how do you solve second order differential equation? You write down the characteristic equation, right? So you replace double prime by r squared. If there's no derivative, it's just a constant. This is going to be your characteristic equation. The solution would be you take the square root both sides, you get r equals to c n pi over 4 plus minus I. Okay? Now, the solution being imaginary means that the solution of the differential equations are sines and cosines. Right? Yeah. Or you can also say, oh, it's e to the this times t and e to the negative this times t, but that's
1.
No, that's the Euler identity. The Euler identity gives you sines and cosines, right?
Right.
Yeah. So that's another way to get it. Okay. But here's what you have. You see that this would be C1 or this A times cosine C n pi over 4t plus B times sine C n pi over 4t. Okay? Yeah, at this point, if you're not clear of how we went over this, please review your second order differential equation. So if you have a constant second order differential equation, the way you solve this is you write down the characteristic equation, solve this using the quadratic formula or whatever, and there are three cases. You might have two reals, which are the easiest case. You might have a double root, so a single real number. And the third case is when the value comes out as r equals to alpha plus minus beta I for some real numbers alpha and beta. And for that, the solution y becomes e to the alpha t, a times cosine beta t, plus b times sine beta t. Okay, that's what you learned in the previous ODE course. You learned this at some point, okay? You may have forgotten. The thing is, here, this is like 0 plus minus Cn pi over 4I, so that's like alpha being 0, and e to the 0th power is just 1, so that doesn't exist. Right? And this is your beta, so that's why it appears here and there. Okay? That's why we have the Cn pi over 4 inside the cosine and the sine. It just follows from here. Okay? Is it good? All right. So just make sure that you know that. If you don't, then it's a good time to review your ODEs. Right? Okay. So going back, because we're doing separation of variables, which says I want u, function u, to be a function of x times function of t. Now we have t times x as the solution, which means the solutions look like a cosine n Cn pi over 4t plus b sine Cn pi over 4t times x of x, which is sine n pi over 4. Oh, put on the next one. X. Okay. Now, these are actually infinitely many solutions. Even for a fixed n, you have two solutions. You have cosine times sine, you have a sine times sine. Okay? And since n could be 1, 2, 3, and any number, you have infinitely many solutions. So in general, what's the most general solution that satisfies both the wave equation and the boundary conditions? What is that? What would you write? You promote this into the sum of everything. You add for all n, 1 through infinity, and these a and b's become, it could be different for each n, so we put a subscript for it. So it's an cosine Cn pi over 4t plus b times sine Cn pi over 4t, bn, times sine n pi over 4x. Okay, so that's what you get from the hard work, but it's not done yet. What should we do next? What have we not satisfied yet?
U of x 0 being...
Right, u of x0 being x times 4 minus x, that's not satisfied yet. And ut of x0 being 0. Those are not satisfied. Now, let me apply the second one first, because that gives you some immediate result. If you differentiate this by t, then cosine becomes negative sine, so it'll be, because of the chain rule, Cn pi will come up front. So negative Cn pi over 4 an sine Cn pi over 4. And then, oh, by the way, we're plugging in 0 into t, so we plug in 0 here. Oh, but sine of 0 is 0, so that doesn't do anything. And then sine differentiates the cosine, so it's Cn pi over 4 bn cosine Cn pi over 4 times 0, but that's a 0. Times, I don't have any room, but times sine n pi over 4x, right? And because sine 0 is 0, that goes away. So what you get is really summation of n equals to 1 through infinity of bn times Cn pi over 4, cosine 0 is 1, and then sine n pi over 4 x. But then this has to be 0, right? Okay. See, this is the some coefficient of the sine function, right? So what this is telling us to do is to represent 0 as linear combinations of infinitely many sine functions, right? So we are asking to find the Fourier sine series of 0. Guess what Fourier sine series of 0 is?
0.
0. So all of these must be 0. And since c is non-zero, n is non-zero, pi is non-zero, 4 is non-zero, the only thing that could be 0 is bn. So from this, we see that all of the bn's will be 0. Okay. So that's nice. We don't have to calculate this much. Now, notice that if the initial condition was the other way, if this was 0 and this was x times 4 minus x, you will be in the hook for calculating the Fourier sine series of x times 4 minus x, and then it's more complicated because that's not directly equal to bn, but it's equal to bn times something else, right? So that's why I set this equal to 0. Right? Okay, now let's plug in 0 into t directly. Then I already have that this is 0, so that's gone. If you plug in 0 in here, what do you get? Cosine 0, what's that?
Negative 1 to the
Negative
1.
1 to the power.
No, cosine 0.
1.
Oh, 1.
1, yeah. Cosine n pi is negative 1 to the negative power, okay? Cosine 0 is 1, so you get an sine n pi over 4x. So what you get is x times 4 minus x equals the summation of n equals to 1 through infinity of an times sine n pi over 4x. And we know that that an is the bn for this. So that an is really the bn from the Fourier sine series. We're trying to find the Fourier sine series of this, which is defined as 2 over L, 0 to L f of x, sine n pi over 4x over Lx. And in our case, L is 4 because it's 0 to 4. So it's 2 over 4, 0 to 4 of x times 4 minus x, and then sine n pi over 4 x dx. Okay, so that's what we have to compute. And once we have that, then we can just plug it in here, right? So let's just erase everything else. The only thing left is to just calculate that integral. If we solve the integral, then we can happily plug it in here. Bn is 0, so we have the solution. All right, so let's do the integral. It's plus minus d integral 4x minus x squared is, if you multiply x times 4, x times x, that's what you get on the d column. On the integral column, you put sine n pi over 4x, and then differentiate, that's 4 minus 2x, differentiate again, it's negative 2, differentiate again 0. Integrating sine gives you negative cosine, so it's 4 over n pi. Cosine n pi over 4x. Integrate again, you get negative 16 over n squared pi squared, sine n pi over 4x. Integrate again, you get 16 times 4 is 64 over n cubed pi cubed, positive cosine n pi over 4x, and then plus minus, and you read off the table by doing that, go across and slant down. And the last one, you have to go backwards, but we don't care because it's 0. So the result of the integral will be, don't forget the 2 over 4. 2 over 4 times x times 4 minus x times negative 4 over n pi cosine n pi over 4x. Okay. And then negative times negative is positive, so it's plus 4 minus 2x times 16 over n squared pi squared sine n pi over 4x. And then finally minus 128 n cubed pi cubed sine n pi over 4, no, cosine n pi over 4x. And then to this you plug in 4 and 0. Now when you plug in 4 in here, 4 minus 4 is 0. So that doesn't create anything. This is gone. If you plug in 4 here, 4 cancels. What sign in pi? 0. So that's 0 as well. So you see that the only thing that creates a non-zero thing when you plug in 4 is this one, which gives you cosine. 4 cancels, you get cosine n pi. What's cosine n pi? Yes. This is negative 1 to the nth power. And then when you plug in 0, again, 0 times anything is 0, so this is 0. If you plug in 0 here, sine of 0 is? 0, so that's gone. And the only thing that creates a non-zero thing is this one. Cosine 0 is 1, but because you have to subtract, it's minus of negative 128 over n cubed pi cubed times 1, and therefore this is like, that'll be plus. So it will be 128 n cubed pi cubed, 1 minus negative 1 to the nth power. So that's going to be your an. Bn is 0, so now we can finally write down the answer. So answer, your uxt is going to be summation from n equals to 1 to infinity of this thing, 128 over n cubed pi cubed, 1 minus negative 1 to the nth power of cosine. Did I mess up something?
Should there have like a 1 over 2 at front?
Oh, forgot that. 1 over 2. Thank you. Yeah, that's like the most common mistake. I've been teaching this for so long and I still make that mistake. Okay, sorry about that. So it'll be 64. Half of 120 is 64. Okay, and then this one, and then cosine c n pi over 4t times sine n pi over 4x. Okay. And again, you can use the computer to plot this for various values of t, and you'll see that this does go like that. Okay? So this is indeed the solution.